Good evening, guys. I'm Shibashish. In this video, I will discuss how to redesign an existing component, which uh, which is meant to, redesign existing component which was earlier meant to be manufactured through conventional process, and redesign it for 3D printing. Okay. Um, so we'll use a tool called Altair Inspire and Inspire Print 3D in this journey of redesign process. And in the next video, what we'll do is we'll take that design which is generated by this process for 3D printing, and we'll actually try to print it in, of course, plastic, and try to see what are the challenges we face, and then rectify those challenges in process level. Okay, so in this part we'll do three things essentially. One is we'll take existing design, then uh, which is meant for casting, and then we recreate a design which is good for 3D printing, what we call design for 3D printing. And we'll um, also do a check using Inspire Print 3D to what will happen if we actually going to print it in metal 3D printer, and what are the problem we might face, the typical 3D printing defects. So without further delay, let's get started. Okay, so this is the tool what I was talking about, and this is the component what I was talking about. Okay, so we see it over here. This component is a aircraft bracket. Essentially it holds some shaft over here, and it is mounted over this three bottom holes through bolt. Okay. So now if you see it over here, you see that this design is perfectly suitable for casting. And if you check the mass of this design, this is around 9.6 kg, so around 10 kg we'll say. Okay, so now let's go ahead with the process of redesigning it for 3D printing. Okay, you will agree that that if we print exactly this same one in Inspire in any printing 3D printing process, then you will end up creating not only a lot of supports which are required for this part to be printed, but also it will not be optimum design, because you will actually spend a lot of material in this design itself. So that's the whole purpose that we talk about design for 3D printing. Okay, so the first step what we'll do is to convert this design. Before we start converting, we'll actually check the performance of this existing design in terms of structural integrity. Okay, so to do that, what we'll do is we'll make sure that we apply the loads and boundary conditions in this in the in the way it should be. Okay, so these are the location where it is actually mounted, and there are three more. Okay, these are the mounting location I am creating, and of course you have to create the loads as well. So in this particular problem, what we are assuming that we are loading this part in there are two loads applied in this part. Both of them is applied to this circular hole over here, mounting location over here. One of them is applying towards y, which has a value of 2000 Newton, and the another one is applied towards z, okay, which has a value of 4000 Newton. Okay, so once you apply that loads and supports to make sure that you are replicating your actual working condition, then you can go and check your baseline performance, what we call that, how it is going to withstand, or how much stress is going to come in this part, in this existing design, and how much displacement it is going to come. And to do that, we will use this analyze option of inspire, and here you will specify your element size, and you will choose the load cases whatever you have created, and then you will run this simulation. And once simulation run is complete, you can check the displacement. You can check the displacement for each of those load cases, and you can also check the stresses. Okay, just to make sure that these are within. I mean, you have to note it down, because after redesigning is complete, compare this new design in terms of these parameters only. Okay, so once we have done this stress study and structural analysis study, now we will start actually the redesign. Okay, so to do that, first thing what I have to do is we have to get rid of this design features. Okay, to convert this design to a design space. Okay, or the package space. And you can of course do this in existing CAD system by taking this to be imported in your CAD system and then fill these pockets, or there is a way to do it over here as well. What you will do is, there is a option called simplify. Before that, let me just hide this connectors over here. Okay, so what we'll do is, we'll remove all these holes at one go. Okay, only don't want to remove just this, barring these holes which are required later for my load application. I'm going to remove rest of the holes. So I'm just deselecting these holes which are not to be removed. Okay, so these are holes which are not to be removed, and there is one more in the top which is a load application point. Okay, rest of the thing I can remove. So if you see that it has removed everything, but again I need this hole to be kept. So what I'll do is, I'll use another feature of this inspire, through which I will I'll keep I'll cut this area over here using this parts. Okay, so I'll again choose this as a target and this as my tool, and then I'll again subtract it. And once that subtraction is done, it will be easy for me to delete the inside pieces. Okay, so let me delete this inside pieces. Let me delete this as well. So now you'll see that I have converted this whole design to a design space, or block of space material which are required. I mean, where my design should not go beyond that space. So that's what is design space. Now again I will apply this loads and boundary condition, but before that I also have to declare this software that this is the area what I want to actually redesign. Okay, some of the areas like this and this I don't want to touch, so those are we call non-design space, and this is what I am redesigning. So that is what is design space. And rest of the things, the load application points as well as applied loads and supports are remain same. Okay, once that is done, I'll define my materials. So here I am choosing same as steel, or maybe I'll choose steel. And then what I'll do is, I'll go over here and define the way I want to redesign it, in the sense that I can define multiple ways to redesign this part, what we in more technical term we call optimization or topology optimization, if you see it over here. And then one of the way of defining the specification of redesign is that we call maximize stiffness, where we can choose the amount of mass we want to keep in terms of percentage. So here I am telling that I want to keep 30% of this mass to be kept after my redesign or optimization. Or I can say that I don't know about mass. What I want is, I want to keep a certain factor of safety after the redesign is done. So in this particular case, I'll go with the second option and run this model. I'll show you how it will look after run is complete, because the run is going to take some time. Okay, so let me open that model which I already run, which is this one. So we see it over here. I did multiple runs with multiple fine tuning of those requirement. So one of them, first one is most important one is this one. Okay, so here what I did is I start with this, and then you run that optimization, and you will get this kind of design. Now you might see that there are some more runner there. What are they? So those are so Inspire gives you option to create redesign. I mean, doing redesign or optimization with some more constraints, what we call controls. So these controls basically governs the way material will be laid out after redesign to suit a particular manufacturing process. For example, I can say that I want to manufacture it through casting, so, or maybe I want to manufacture through extrusion, or maybe I want to have certain over angle. So all those things I can specify, and if I do that, if I specify all those things, I will get different kind of results. So for example, I will get a casting kind of results from here, okay, or here. Okay, so that's where we got different kind of optimization result. But the most important one in this particular case is this, because I don't want any constraint to put, because I simply want the most optimized design, because I am going to manufacture through 3D printing. Okay, so this looks good, and if you see it over here, it gives reasonable material saving as well. Then I can check this check the final geometry out of it. So I will definitely not print this rough model. What I will do is I'll detail this model, and then I can go to print. To detail the model, there is a option over here what we called polynubs, okay, which will allow you to create a detailed model which is much smoother after you finish tracing like this. And at the end of the detailing, we'll get a shape which is something like this. Okay, this model looks good, and this is bionic in nature, and we can think of printing it. Okay, but before that, let's see that how it is performing in terms of structural strength. Okay, so let me just write these things. Okay, so if you see it over, I have again done the analysis of this model and tried to see whether I am crossing my limit of stress and displacement. In this particular case, it is not. So I can directly go and print this part over for 3D printing. But when I think of 3D printing, I have a challenge over here, and that is what we called overhang challenge. If you see this holes over here, if I going to print it like this, so there are many holes which will require many cutouts, which will require a lot of supports, this particular areas and this particular areas. So to avoid that, again there is option in Inspire over here, where, as I said earlier, if you can remember, that there is a shape control which we called overhang constraints. Okay, I can apply that overhang constraints in my design space. So I'm going back to my design space. Okay, so let me go back to my design space. Okay, so this is my design space, and I applied a constraint which we called overhang constraint. And in that overhang constraint, what I'm saying particularly is that I can specify the direction of printing, and I can also specify the overhang angle. and if I run this model, it will give me the design which is which is uh, which is fulfilling that requirement, and we will see that there is a uh, completely different design than what we got previously. uh, and here you will observe that it requires actually much lesser support than the previous one. So what we did is we thought of detailing this. I mean, we thought of going ahead with this model for printing. So we detailed it again like in polygons and using polygons, and we got this design. This is the design what we got. So looks good, and if we print it in this direction, it will not take much support other than this end areas. So we'll see that how it works. So to check that how much support it really needs and how what will happen to print, what we'll do is we'll change to the module what we call print 3D. And in this print 3D, what we do is we can define all the printing, whole printing operation. Okay, so how to do that? So the first step is you define your materials. So you can define the materials which are common, and please remember that in this print 3D we simulate only the metal printing. Okay, so you can define materials which are very popular and which are already listed. If you don't find your material, then you can even edit your material provided you know the properties of the new material. Okay, so once your material definition is done, you can choose your machines. So by default there are these three machines listed. If you by means of machine, it will choose the machine bed. So for example, if I go to US, particular model of US, it will choose the bed, and it will also choose the laser parameters. If nothing fits to your part, then you can probably choose your default value. What it will do, it will try to take the shape of part, and it will try to create the bed as per accordingly. So once that is done, you must remember, you must observe that this is not what the intended printing direction for us. Okay, so you have to rotate this part, or in other word, we have to orient this part. To orient this part, what we'll do is we'll go to this next step, which we call orientation. And in this orientation, there are some predefined mode of orientation. For example, maximum build height or minimum build height. So if you see that this is maximum build height, and each of this orientation will highlight the area where you need support for this particular build. Okay, orientation, and it will also tell you that what are the support volume and printing time, expected printing time for this particular orientation. Okay. So once you have that, you are happy with the orientation, you can go to next step where actually you will create support, and based on your orientation, it will Inspire will generate support for you. That's the actual CAD model. Of course, if you have your own support created in CAD, you can bring that and tell Inspire to use that as well. So if you see it over here, I um, this is what the print and this is what the support it is created. And once that support is created, you can actually check the slicing of each of those layers to make sure that you are not creating very tiny layer, because otherwise there might be a problem of joining with the subsequent layer. You just have to make sure that you are not creating very small layers over there. Okay, and once you are happy with that, you can go for simulating this whole printing process. Okay, what all you need to define those velocity, laser power, power reduction, and some more parameters, and you can also adjust the between speed and accuracy over here. And after that, after you run this simulation, you will able to see. Let me show the results over here. Okay, so this is the result. So it's just loading the results in the background, because this printing simulation takes longer time, so it creates quite a big file, and which if you reload, um, it takes some time to load. So that's the process it is doing. So what it is, in the back end, it is trying to pull out all the result data and try to create those contours for this particular example. And it always save the required information, although you it is for this particular part. And there is another feature which is a run history. If you see it over here, which kind of help you to bring down your any of the result what you did previously. So if you see that this is what it does. So it starts printing, and in each of the layer, while printing, it tries to give you the respective displacement, strain, von Mises stress, as well as temperature values. Okay, so and this does not end when the printing end, but it goes on till the time it after printing it goes for cooling, and again after cooling it goes for support removal. So all those three stages are covered, and if you will see the animation that after some time the support will be removed. And if you observe very closely, let's take any particular example of over here. If you see that I am tracking the displacement, and let's go till some steps down. Okay, so this is my printing. So my printing is complete now. We'll see that displacement is around 0.3 mm. Now if we go further, some steps further, so if I say some steps further, we'll see there is a change in the displacement value as it is tried getting cooled. Okay, and you would expect further reduction when it actually the support is removed. So you'll see that it has changed a lot. Okay, so with this after you are happy with this result, you can export this model in terms of either CLI or STL format and send it for printing. Okay, and what I'll do in the next video is that I will take this export of STL, and I'll try to use my small FDM printer, which is a plastic. Of course, this is not metal, but the aim over here is to gain as much as insight as possible for the printing, and we'll also see that what are the problem you face other than this whatever has been simulated, and how to solve those problems while you are doing printing. So this I will end this part of the video over here, but please visit my next part for the remaining portion of this interesting process of redesign. Thank you very much for watching.